data sets and value data sets. And even sitting with the GA, I don't even know how to do those. So I just would request if we could just have that part of the
Just the data sets?
Yeah.
I think that's fine.
I think I'll just make it a lot easier. So it's not even part of the algorithm, it's just part of the schedule.
Okay, I mean, it's pretty straightforward. I think.
Not to me.
Okay, that's fine. I think that's fair. Sure. I want you to focus on the interesting stuff, not the uninteresting stuff. So I'm happy to. Yeah.
Why did they, in the RL Adventure 2, why did they have the actor and the critic in the same loss, or in the same gradient?
Okay, so RL Adventure, well, so that's kind of the canonical way to do it, is you have a single loss function that involves terms for both the actor and the critic. And then if they happen to share parameters, gradients kind of do the right things. If they don't have to share the parameters, the gradients still do the right things. So it's just a little bit more general. That's my understanding.
So when to combine them?
Combine them. So if you yeah.
But you don't have to.
No.
And then if you don't have to combine them, where do you put the little entropy? There's the entropy term on the loss. Do you put that with either or both?
The end of the video talked about that. Like we didn't get to that, but you put an entropy, so like it's just another thing to help with. And it's a combination of like both things with entropy. It's like and you can like set hyperparameters to say how much entropy I want in the distribution.
Yeah, I'm pretty sure we didn't use entropy at all.
In your implementation?
I have to go check.
Yeah, so if you combine them into one, you can add the entropy in there, but you don't have to.
Yeah.
You don't have to. The end of that video explains it.
Yeah, and for anyone that was curious, the actor and the critic are the policy network and the value network.
Yes. Sorry, that was unclear. Good. Yeah.
The actor and the critic are the policy
Yeah,
network and the
it
value
seems
network.
like that the
In their
RL
implementation.
Adventure, they always have a normal distribution. Did anyone else see that? It's like always normal.
The Gaussian?
Yeah, for the distribution that it produces for the policy. Or
Okay.
something like
Yeah,
that.
could be.
Is that like,
So yes, that's perfect. So I've actually been through the RL Adventure code deeply. I just glanced through it and it's fine. That would be true probably if it was a continuous action space. Then you would want a continuous distribution over that space. And Gaussian, you should always just start with Gaussian. So probably the network outputs the mean and the variance of the Gaussian and then the policy sample from that.
yeah.
Okay, good.
Is the reading on Learning Suite like all up to date?
Yes, so I updated the Learning Suite reading. So there's one, since I'm giving it to you so late, there's only one required reading for this class, for this week. And that's a paper called Defense Scan, which we'll talk about why that's relevant after today. And then there's an optional reading, if you care.
And for next week, that's not new reading?
Oh, that's not up to date.
Okay, so
Because I just switched it around, because I decided we're going to do the neural Turing machine and the VNC next week. So it's in honor of Thanksgiving.
So kind of going back to the whole Gaussian idea.
Mhm.
So in our case, since we're working with, in the very basic case is the balancing one, there's only two actions left.
Right.
I was thinking of doing a softmax, which would give you a natural probability. Do you have
Yes.
to worry about Gaussians and trying to go?
Well, yeah, so in that case, I forget if so if you have a discrete action space, you need to output a discrete set of probabilities. So you can't use a Gaussian in that case.
Okay.
It's type error. I think there's different versions of cartpole. Cartpole is interesting because as a minimum time, you can also think of it as a minimum time control problem. And the solutions to minimum time control problems are always the extreme control values. It's called bang-bang controller. And so I think you can get away in cartpole, even if you think about the pole as a continuous amount of torque on the cart. So you can think of it as a continuous control space, but we sort of know by structure of minimum time control problems that you only need the extremes of the control values. And so that's why you can parameterize it with discrete set. So. So, okay, good. Any other questions? All right, we'll have fun with it. I expect competitive Dota 5 agents by Monday. So,
We'll win this time.
all right, good. Okay, so today and next week, what I wanted to talk about, as I've said, we've begun to segue now. So we're going to finish up. We're done with DeepRL, and we're now segueing into other topics about deep learning that I think are relevant and that I think are potentially useful for you. So we've talked a lot in this class about the successes of reinforcement learning, all the wonderful things that it can do. But one thing that we haven't talked about very much is the weaknesses of reinforcement learning. And so I thought we should give at least one lecture on the subject. And so today I'd like to tell you about adversarial perturbations and what they are and why people find them super interesting and why I think it's, well, it tells us a lot, not only about weaknesses of deep learning, but also about how deep learning accomplishes what it accomplishes. Okay, so here's the idea. The idea of an adversarial perturbation is very simple. You take an image, say it's Panda, you train some classifier, some awesome GoogleNet, ResNet, 1,000 layers, whatever, and you get some awesome performing network, and it classifies this as a Panda with high confidence. You then add some noise, very carefully chosen noise, but the noise is essentially imperceptible to human eye. You can see it a little bit here. It's actually kind of hard, but this noise is around sort of like 1 or 2 pixel values worth of noise. Okay, so it's very subtle noise. In fact, the noise, you can see like JPEG compression artifacts here that like are way noisier than the noise we're adding. And yet, adding this super subtle noise changes your awesome network's classification from Panda to Gibbon, also with super high confidence. 99.3 confident, that is a given. Now, of course, you and I look at that and we're like, still a Panda, bro? Like, I don't know. So it's kind of funny, but we don't have this problem. At least I don't think we do. I've never, it'd be super interesting to find out if humans are subject to the same kind of thing that's going on here. Okay, so, oh, by the way, if you throw this noise into the classifier, it's classified as a nematode, but with 8.2% confidence. So like the network's like, I don't know what that is. Like, nematode? Not sure. Okay, so this is called an adversarial perturbation. Someone, an adversary, has taken your awesome classifier and is able to fool your classifier, and is able to fool your classifier reliably. And what we'll see is, as we kind of go through this lecture, we'll see that this is a surprisingly deep and difficult to deal with phenomenon. Okay, by the way, so how was this noise calculated? Let's see if we can, what is this, what do you think this means? Okay, first of all, what does sine mean? Take the sign. So it's plus or minus, so this is like binary noise. But it's binary in RGB. So probably what that means is it took just one pixel value, okay? It's either a +1 or a -1 for every pixel, RGB. So we get this colorful noise. What's this? Gradient of something, yeah, something like Jacobian. Okay, so in this particular adversarial example is calculated by asking how do we have to perturb the image in order to maximize the change in the output of the classifier. Okay. And so you're taking a step in a very specific direction, but it's a very small step. So what does that tell you about the decision boundaries of the DNA? Something steep, right? It's like we have this space, and you and I think that Panda image is like, that is not like there's no question in our mind that that's a Panda. And so you can imagine, like, I tend to think of that Panda as being in the middle of Panda space, where you can take this image and you would have to perturb it a lot to convince me that that is a given. But somehow the network doesn't see that. Somehow the network, it's more like this Panda image is right on the edge of Panda space. And if we just push it just a little bit, then all of a sudden we're in Gibbon space. Now, you have to push it in exactly the right direction in some, I don't know, million-dimensional space. But yeah, something about the shape of these decision boundaries is a little bit funny.
So it says that with the sine gradient Jacobian thing,
Yeah.
the theta in there, is that like the parameters of the network after running the actual regular panda image through, or is that something else? Like, does this require running the image through the network in order to be able to generate this noise?
Okay, so in this particular case, yes.
Okay.
But we shall see. We shall see many variants on this, which you're like, wait, that seems unfair. So yeah. Okay, go ahead.
And isn't there a little bit more? Because not only did it put in given space, but like we're very high contrast.
Right! It's like in the middle of given space, sort of. I mean, we're not even sure what that means anymore. Because apparently 99 or 57.7% confidence panda space does not mean it's in the middle of panda space. That means it's like on the edge and we just don't happen to know that there's an edge. Or something like that. Yeah.
Well, I mean, 0.007 might be a pretty small factor, but when you're moving 0.007 in that many dimensions, it's still going to have a really significant impact.
Yeah, somehow, right? Somehow this is having a really significant effect, even though to us it's basically imperceptible. Yeah.
It kind of feels like that colorblind test, where you have two numbers, but if you're colorblind, it's one number.
Oh yeah. So there's like something in, or maybe it's like an optical illusion, right? There are bugs in our visual system, and if you show us just the right visual input, like weird things happen to us. Maybe something like that is going on here. Maybe that's our version of this. Okay. So by the way, this is not unique to this style of noise. It's a little bit of a tangent, but there's this fun paper that said, let's see if we can find other images that fool neural networks. So a guy used an evolutionary algorithm, so think genetic algorithms. And what he says is okay, take some images, put them through classifiers, right? You can classify them okay. But what if we used an evolutionary algorithm to just like sit there and search for interesting images that the network misclassifies? You get the idea? So we're just going to, and he has some operators that like take images and do random weird things to them and generate kind of odd things. And so these are some of the results that they came up with. So African chameleon, vacuum cleaner, accordion, digital clock. And some of these you can kind of maybe see, like ski mask.
Car wheel is like
The bagel.
it's a circle.
Bagel. Oh yeah, bagel. That's not compelling. Yeah, car wheel. Like, well, I guess I can kind of see circle-y sorts of things.
Monarch butterfly, the bottom right.
But like comic book, yeah. I mean, so it's interesting that neural nets. Again, you and I don't seem to have this kind of a failure mode. Something about shipping just the right inputs into this neural net causes just the right neurons to activate just the right ways, and like all the linear algebra just works out, and bing, you get some weird classification.
I mean, for all of these images, though, I mean, what do you expect the network to classify as? Because it hasn't been trained on these types of images.
Well, right. So, yes. Okay, so good question, good point. It hasn't been trained on images that look like this. What would we expect? Well, I think what we would expect is yes, it has to give us an answer, but we would hope it would be a low confidence answer. We would hope that the network would say, like when it spits out its probability distribution, it would essentially be uniform instead of being highly peaked. And that's the problem. It's confident about it, but it's wrong. Yeah. Okay, so these results come from this collection of hacks. Somehow we're maximizing a neuron's response in this very odd kind of way. And the things that seem to do it to neural nets are extreme pixel values, so really big or really black things, and then these weirdly structured high frequency patterns. Okay, so why does this happen? So here's like the basic method. It's called the fast gradient step method. And it's really, really simple. You just start with a guess, and then you start adding noise. It doesn't even have to. So what's interesting about this method is you keep adding noise until until the classifier misclassifies it. Now, there's this image here. Let's see if we can parse this image. This is a figure. I should zoom in here. Hold on. See if I can do it. Typing in PowerPoint when it's full screen is always tricky. Is that helpful? No. That helpful? No.
Can't you zoom in and then move?
Stay by. Old fashioned. Okay, that's slightly helpful. Okay. So this is. Okay. So this image comes from this paper, which talks about the FGSM method. Sorry. And what this is showing a bunch of decision boundaries over here. So different colors represent different classes. And if you, what this is saying is if you move, so this is like it's like the legend, right? So you imagine we're kind of in the middle here. And we've kept adding this noise until we get to a decision boundary. And then if we take a step, one more step, it'll cross the decision boundary and our classification will change. Does that make sense? So if we're here and we take one more step in the direction that FGSM has told us to go in order to misclassify, we're going to switch over and hop into a new decision boundary. But the point of this figure is just to illustrate what do you notice about these decision boundaries? In general, yeah, very abrupt and they look like vertical. And so it's like if you go up to the edge of this decision boundary and then you look in either direction, it's like this wall of a decision boundary. And you could go a little bit over here and then cross, and you'd be crossing the same boundary. So these decision boundaries are very sharp, they're very definitive, and they're easy to find. And they're not that far away from any given image. Okay, so let's talk about some variants of this, if you thought that was depressing. Okay, so not only does it work on directly perturbing the inputs, you can also do things where you construct an attack. So sorry, these are called attacks because people in cybersecurity are super interested in this. Why would cybersecurity people be interested in this?
Self-driving cars.
Self-driving cars. Okay, why is this an issue for self-driving cars?
Put it on a stop sign.
Stop sign, the car will flow through it.
Okay, yeah. So the thinking is something like, well, if we use a deep neural net in a car, self-driving car, and the deep neural net is like doing our perception, and it's looking for stop signs. What we don't want is for somebody to put a sticker on the stop sign that's an adversarial perturbation, and suddenly the car essentially can't see the stop sign. Right? That's the problem. So, and you might think that's a little far-fetched, but it turns out that these adversarial perturbations are surprisingly robust. So first of all, you don't need access to the original model in order to construct them. That's weird thing number one. So if I train a ResNet, so let's say Google has or Waymo has their awesome deep neural net, which is a stop sign detector, and I want to fool it. All I have to do is train my own neural net, find a perturbation from my neural net, and it will transfer to other neural nets, even if I don't have their topology. They're surprising, they're like that robust. Not only can you transfer them, you can transfer them through corruptions that come from the physical world. So here's an image from the data set. And what they did here was they took a picture, they printed out the perturbation, or they perturbed the image and then took a picture of the perturbed image and still misclassified it. Okay. You can also there's also something called universal perturbations, which we'll talk about in just a second. Go ahead.
In order to fool a different neural network, do you have to train on the same data set?
That I don't know. There's some evidence, though, that these will even fool different types of classifiers. So let's suppose Google doesn't actually use a neural net. Let's suppose they use a sport vector machine or something. Turns out the perturbations can also, some perturbations can affect those as well. So they're it's surprisingly hard to get around this problem. Yeah.
So this is going back a little bit, but when we were talking about how that neural net in the last couple of slides was very confidently misinterpreting, like misclassifying images, is there? It occurred to me that for very well-trained neural nets, there might be an inherent reward for being confident, right? Because if
there
a
is,
neural net
right? We want it to classify things confidently.
Yes, we want it to classify things confidently, but if a neural net is right 95% of the time over all of the classes, then there's an inherent reward to the net, regardless of the class it's looking at, to predict it confidently, right? Because if a neural net isn't wrong very often, it's never going to be hurt by being confident.
Right.
Right. So there might actually be an inherent reward to being confident for nets that have been trained for a very long time.
Yes. Well, I mean, that's baked into the loss function. The more confident it is about right predictions, the lower the loss.
Yes.
Yes. But we try to set up the loss function so that when it's wrong, what we don't want is the loss function is specifically constructed so that confident but wrong predictions are like super strongly penalized.
Yes.
But we'd much rather have it give a not confident right prediction than a super confident wrong prediction.
Yeah. But
And the loss function does that.
Yeah, my point is that if you train a net long enough after it started being right the majority of the time, then it might not be penalized for being confident on a wrong image.
Oh, I see. It might not learn the disadvantages of being.
Yeah, I mean, so initially, of
I
course, it's
see.
going to be wrong, and
I
if
see
it's
what you're
confidence wrong, it gets penalized. But once it's right,
It's forgotten what it's like to be wrong.
Yeah,
It's so smart.
Once it's right 100% of the time, then
It's like
there's
a
an inherent
professor.
reward.
Sorry.
So that's what I'm trying to say. Is
Yeah,
that
that's interesting.
We'd have to find a way to penalize.
Yeah.
Introduce new images or things.
Teach us some
Just
humility,
right.
right? It's its pride that's been its downfall. Yes. It's interesting.
Label smoothing might help with that.
If you can write a paper that cites some Alma scripture, just subtly, some footnote, yeah, that'd be awesome. Do it.
Okay, so then couldn't you account for this and train your neural network to beat these things and to not have strong, sharp decision boundaries?
Okay, yeah, so there's a whole question of how you defend against adversarial perturbations. Lots of things have been tried. We'll talk about some of them today.
That will never work.
So the short answer is, it is not enough to generate your data set, train your network, then go and generate a bunch of adversarially perturbed images, train on them as well, and hope, because it's just as easy to construct new folding adversarially perturbed images into your training only fixes that one direction. But there's basically an infinite number of these directions. So yeah, that's the problem. I thought it was fun. There's a 3D version of this. So here's a turtle, it's a 3D printed turtle, and if you have the normal turtle, it's confidently classified as a turtle, there's this little video here, which you can watch if you care. But they then colored the turtle with an adversarial perturbation, and then they threw a classifier on it, and it was a rifle. Sort of no matter which direction you looked at it from. So I think this is the flip side of the dangers of these adversarial perturbations is one thing you can do is convince the self-driving car that the stop sign is not a stop sign. But the other thing you can do is convince a security robot that that's actually a robot. That's a weapon. Right? So that's in either case, if a neural net is making decisions based on these inputs, then this is a concern. So a lot of people are kind of worried about this. By the way, this I thought was interesting. So you have to think a little bit harder about how to make it so that the adversarial perturbation works for any given viewpoint. But you can also kind of imagine that Well, we just change our optimization a little bit. So the way they came up with this was this expectation over transformation. And so the idea was, instead of trying to find just one direction, and just happens to be like the nearest direction, let's find a perturbation that is robust against all of these possible transformations. In this case, they're thinking about transformations that come from the way that a physical object can be viewed multiple ways as it translates in 3D space. But you can also imagine other classes of transformations. So for example, contrast, brightness, saturation, coloration, lighting. You could construct, using this technique, a perturbation that's robust to all of those things. Yeah.
So when we're training networks, a lot of times you use things like you add noise or dropout in your network and things like that. And then when you're actually, you deploy that model, you don't do dropout. But
Right.
in this case, like, could that protect against things like this?
Yeah, so that's a good question. I think dropout does not protect against it, but I do, I'm not an expert, but I seem to remember that things like dropout help. Precisely because it's a little bit harder to convince them, like to come up with crazy weird patterns of neurons lining up. Sort of precisely because the network's been trained to be robust to weird combinations of neurons existing or not existing.
Well, like,
But I seem to remember it's not a full defense. So I'd have to look at the answer though.
Because there was a paper by like Michigan State where they were driving to the stop sign and had the sticker and it like proceeded as a 45-mile-an-hour sign until it's really close. But like, you know, convolutions will find that like those features anywhere in the image.
Yeah.
So could you like scale them? Because maybe when it's like farther away, you know, it sees like it doesn't like putting a limit on like I guess the scale of the images, input images.
Yeah, maybe. Yeah, you're referencing something, maybe you didn't catch this, but some researchers figured out that it's enough, you don't have to corrupt the whole image. You can just like print out these stickers, they're like this big, with some crazy pattern on it, and just slap it on things, and the network then classifies the whole object as that thing. Yeah, it's super frustrating.
When they were perturbing the turtle, did they know that permutation was going to give them a rifle? Or is there a way to calculate like specifically what types of things that you want to classify it as?
Yeah, I think, so it is, so I think if you want the minimum possible perturbation, it'll just take you to some crazy class, and you probably don't get to say which one. But there's no reason why you can't just draw a line. So you imagine we're at some point in the space here, there's some decision boundary to the class that you want, and you just take a step, sort of the minimum step necessary to cross into that territory, typically. So yeah, I think you can pick. With the universal perturbations that we'll see in a second, that's not the case.
Would it be possible to train a image classifying neural network that trains on like 3D models of objects? Because I feel like a lot of these problems arise in the fact that they're training on 2D images. But what if they trained on like using like an animation software or something, like a 3D model of an object or something like that? Maybe like understand better about how the object is like looks like in real, like in 3D shape rather than like a 2D pictures.
Maybe. Remember, we don't actually, like humans don't perceive the world in 3D. We have two 2D cameras.
Right, but we understand the objects in like their 3D shapes as well.
But we can.
But we
walk
did
around.
that from a bunch of 2D data.
Right.
We do have time, which these networks don't have. So, I mean, I think you're right. In some sense, our representations are much more based in physicality because we have to interact with things and we have to not bump our knees and we have to pick up things to eat and such. So we build representations that mimic the three-dimensional structure of the world, which these don't have to do. It's entirely possible that forcing it to come up with more geometric representations somewhere inside would regularize this problem in some interesting way. But I don't think anybody knows how to form. I don't think anybody's tried that. But it could be cool. Let's go do it. Great final project. Yeah.
Is this mostly unique to like the 2D compositional image network topology, or is it like do these adversarial perturbations show up all over in different sense? Like if you're doing like a translation or like an audio to words, I don't know, do these same perturbations apply in
Other
non-image
domains.
classifiers?
Yes, I think so. So I think certainly in an audio classifier you could come up with these. Could other things as well? I don't know. Like some natural language translation thing?
Yeah.
Is there some weird sequence of characters you could give it that would cause it to output arbitrarily weird translations? Yeah, I don't know. I'm not sure anyone's looked at
But it's
that.
not like a classification quite as much, maybe, so.
Yeah, it's a little bit different.
Yeah.
So I don't know.
I know that people have found and posted all sorts of weird edge cases ever since Google switched their translation to use neural nets, and where you can enter in particular patterns of words, and it will just give you completely bizarre results. So I
Maybe.
imagine it's something similar going on. Yeah.
Maybe, yeah, you've hit the boundary of weirdness and undefined, divided by zero sort of thing. Yeah. So anyway, the point is here, I just wanted to just make the point that here, kind of what they're doing is they're just picking a direction which in expectation is going to perturb the classifier, and where that expectation is taken over some set of possible transformations. And you can do that for any set of transformations. And so you can do that also for 2D things. So here's an example of that where, let's see, so if we can remember this. So here's, the original image, Persian cat. We're perturbing it in different ways. So we're zooming in, we're rotating, in different ways. There's little artifacts here. But under all of these cases, the probability of the true class is very, very high, except in this case, because you can't see the face. But then you can construct the adversarial perturbation by thinking of the expectation over transformations. In this case, transformations are not 3D transformations, they're just 2D transformations of the image. And if we figure out the adversarial perturbation in these directions, then the probability of the adversarial class is highly confident across all those transformations. So in other words, we can make the perturbations robust to arbitrary classes of transformations. That led to the idea of universal perturbations. So the idea of a universal perturbation is it is a single piece of noise which, when added to essentially any image at all, messes up your classifier. Okay, so here's all of these images which are confidently classified correctly, and this mystical little piece of something. And so the flagpole becomes a Labrador, and I can't even read that. What is that? Lycanid becomes a griffin, and the balloon becomes a Labrador, and the joystick becomes a Chihuahua. That's awesome. So yeah, right. So you're like, wow. Okay, so not only so we can find these universal directions, which and so let's try to visualize what that looks like for just a second. What does that mean in terms of classification boundaries? What's going on? Essentially, anything you give it now is wrong. Can you visualize that in your mind? What must have happened? Yeah.
Could it be something like our classification, our boundaries always encompass like very small areas, like the area encompassed by a decision area is very small. So whenever you step, you're always stepping off of whatever one you're.
Yeah, something like that. You're always close to a cliff edge in some direction. And if you only have, we think about ImageNet classification, we're like, oh wow, there's like 10,000 classes. But 10,000 classes, we have a million dimensions to play with here. And so there's cliff edges everywhere. And so it's actually kind of easy to find a cliff edge that will take us off the edge of any given decision boundary off into the nether world.
How hard is it to find like universal perturbations? Is it like they only found a few of them, or is it many things are?
Here's the algorithm, and here's a little diagram kind of explaining it. So it's not super hard. I mean, you have to like work at it a little bit, but let's see if we can understand it. So there's a great video about this, by the way. I gave a really nice talk. This is from CVPR just a year or two ago. So let's read through this. So we take data points and got some classifier. Sit up here. So you can tell me how big you want the perturbation to be. Probably the smaller, the harder it is to find, but that's a hyperparameter here. Okay, so we're going to output some vector v, which is going to be this mystical piece of noise. So we start with 0, and we're going to say, okay, while the error of x, so while we haven't perturbed, like while we're still classifying things too well, then we'll go ahead and update our perturbation vector. So what do? Take a bunch of data points. For each one, we say, what does this say? Translate line 6 into English for me. Yeah, go ahead.
If your perturbation doesn't leave the class, is that what it's trying to say?
Yeah, so if, for data point xi, if we added v and it didn't change things, sorry, so in other words, the classifier before perturbation and the classifier after perturbation give us the same answers, then we didn't perturb things enough. So what do? Compute the minimal perturbation that sends it to the decision boundary. So we want to minimize over r, which is some delta here. We want to minimize the norm of that thing such that k of the image plus our current perturbation plus the new little perturbation of the perturbation changes the classification boundaries. Just want to like maybe run a little optimizer or something. Okay, and that's gonna march us off to the decision boundary. So now we know that we're gonna classify xi incorrectly. And then we just go ahead and update the perturbation. And they have this little operator here which aggregates multiple perturbations together. And kind of the intuition is given here. So you start off with all these decision boundaries and you start just moving to the edges of them with a bunch of different data points. And eventually you get to a point where everything is misclassified.
Does this, and if so, how, work without having the weights or the network architecture? Like, I don't see how this could work without just running it through the.
Okay. Yeah. So, so remember, how does FGSM work? So FGSM, that's the fast gradient step method. What it said if you want to misclassify an image, you don't have to be able to take the gradient. You just add random noise, and you just keep adding random noise, a little more, a little more, a little more, until you cross the decision boundary. So you could totally do this if you had API access to Google's image classifier. You don't have to have the weights, and you don't have to be able to backprop through it. You can just like start adding stuff until you cross the boundary. And that's all that's required for line 7.
So you do need access. You need to be able to.
You have to have access to the classifier.
Yeah.
Except that.
To perform inference.
Except for this result that perturbation vectors calculated on one network actually transfer surprisingly well to others.
So you would need to know the architecture to like try to build whatever Google's doing on ImageNet, right?
Well, so.
Or you could just think of some other, as long as it's trying to solve the same problem, then it works.
Well, of course they have to be solving the same problem.
Yes.
But so here's the result from the paper about this generalizability across architecture. So let's see if we can parse this. So let's look at table 2 here. As I recall, okay, yeah. So rows are architectures for which perturbation is computed. Columns are the sort of the thing we're transferring to. Okay, so I train a perturbation on VGGF, and I test it on VGGF. I get a fooling rate. Like I can basically fool everything. Like I can change I can fool the network on every 93% of images. But I can take the same perturbation for VGGF and try it on Caffe or GoogleNet or VGG16 or ResNet 152, and I'm still able to fool it half the time. So it doesn't matter what Google is, what their architecture is, as long as I can train on my own architecture at home in my basement and then fool.
So the only requirement is that they're solving the same problem.
It's all they have, yeah. Like just as long as the inputs and outputs are the same, then we're good.
That's so bad.
It's, yeah, right? It's super annoying. Okay, go ahead.
Why are people publishing about this, not trying to keep it secret?
I mean,
this is good, right? Open,
This has
the
security
openness of
rules.
academia.
Like image terrorists that things on.
Well, I think it's precisely because people are excited about using deep neural nets for high security, high impact applications, but they're not quite there yet. People feel like now's the time. Like, we need to be aware of this issue and preempt it. Like, if it was 10 years from now and people figured this out and people were actively using DNNs and all these high mission critical, super secure, like, then image terrorism might be a thing. Might be a thing. But it's not right now.
So far we're going back.
So it's good to get ahead.
For real things
I think, no, I think the community's right. Okay, take some comments over here. Go
Went
ahead,
out there
Brett.
in like California and like start like police.
Has there been any research in, continuing to train VGG on images that have adversarial perturbations?
Yeah, it doesn't help.
It doesn't help.
No. Because they're so small. And like I said, it's just, yeah, sure, you fix that one dimension of perturbation, but there's a million other dimensions to travel in.